we have been discussing the chapter called equilibrium, right? So what are the stuffs we have discussed? Sendamichelvan, Sharmila. Kana, what are the stuffs we have discussed in last class? Okay, right. Sendamichelvan?
The previous week we had a quiz, ma'am.
Okay, I'm talking about the last chemistry class of mine. We have been discussing equilibrium chapter, right?
Yes, ma'am.
In that, what are all the stuffs we have discussed? So we have discussed what is reversible, irreversible, and equilibrium reaction, right? And we have discussed what is equilibrium constant, how to write equilibrium constant, and we can express equilibrium constant in terms of concentration and partial pressure. And also we have discussed the relationship between Kp and Kc, and we have seen a couple of problems related to that, right? So what is the relationship between Kp and Kc? What is the relationship between Kp and Kc? What is the relationship between Kp and Kc?
Ma'am, Kp equal to Kc RT power delta Ng, ma'am.
Kp is equal to Kc into Rt power delta Mg. Very good. What is R? What is R? What is R?
Gas constant, ma'am.
Yes. So, as far as the values of R's are concerned, we have few R values based on the different units. And in this chapter, we have to use the R values which have the unit of pressure. For example, R value can be 0.0821 liter atmosphere per mole per Kelvin. Another R value is 0.083 liter bar per mole per Kelvin. And the relationship between Kp and Kc is Kp is equal to Kc into Rt power delta Ng. So by using this relationship, if we have the value of Kc, then we can find the value of Kp. Or if we have the value of Kp, we can find the value of Kc. And what is delta Ng? What is delta Ng? What is delta Ng? What the small n represents, it is the number of moles, right? What does this delta represents? Change in number of moles. What does this G represents? A change in number of moles of gaseous species, right? So what is the expression, Kana? Number of moles of gaseous product minus number of moles of gaseous reactants. Okay. For a reaction, when Kp will be equal to Kc. For a reaction, when Kp will be equal to Kc. When Kp will be equal to Kc.
When delta Ng equal to 0, ma'am.
Very good. If delta Ng is 0, then Rt power 0. Anything power 0 is 1. So Kc into 1 is Kc. So Kp is equal to Kc. That's it. So we'll see one problem here. At 450 Kelvin, Kp is given as 2 into 10 power 10 bar for the given reaction. at equilibrium. What is Kc at this temperature? So for this reaction, Kp is given and we have to find the value of Kc. And what is the formula? Kp is equal to Kc into RT power delta Ng. Kana, could you please tell me the value of delta Ng? Number of moles of gaseous product minus number of moles of gaseous reactants. So we have only one product here, which is sulfur trioxide, which is in gaseous state and whose number of mole is 2, right? So number of moles of gaseous product is 2 minus, we have two reactants here and both the reactants are in gaseous phase and total number of mole is 2 plus 1 3. So 2 minus 1, which is equal to minus 1. So Kp is equal to Kc into RT power minus 1, right Kana? So Kp divided by RT, which is equal to Kc, am I right? So Kc is equal to Kc to be calculated, and what is the value of Kp, which is 2 into 10 power 10 divided by what R value we have to substitute here? What R value we can substitute here? Here the unit is in bar, so we have to choose the R value whose unit in terms of bar, right? So it is 0.083 liter bar per mole per Kelvin. So 0.083 liter bar per mole per Kelvin. Okay. What else? What is the temperature? What is the temperature, Kanna?
450 Kelvin, ma'am.
450 Kelvin. That's it. So we have substituted all the values, right? Could you please tell me the value of Kc? Please come up with the approximate value. That is enough. And now once again, actually here RT power minus 1, right? So if we take this RT to the left side, still it is going to be RT power minus 1. So I can bring this denominator to numerator, right Kana? Or I can write it as Kp into RT, which is equal to Kc, right? So instead of this denominator, I can write it in numerator itself. So into, what is the value of R? 0.083 liter bar per mole per Kelvin and temperature is 450 Kelvin, which is equal to Kc. And here unit of Kp is bar inverse. That's it. So here bar and bar inverse will get cancelled. Mole and Kelvin and per Kelvin will get cancelled. That's it. So the final unit will be liter per mole. So what is the value of Kc? You have to multiply 2 into 10 power minus 10 with 0.083 and 450. Please come up with the approximate value, Kanna. Yes. Sendamal Chelvan's answer is 7.47 into 10 power 11. Yes, this is the right answer. So, by using the relationship between Kp and Kc, we have solved this problem. Okay. Now we'll move on to next question. Here, any doubt? Any doubt till now?
No, ma'am.
We'll move on to next question. Nitric oxide, whose formula is NO, reacts with Br2 to give nitrosyl bromide as per the reaction given below. Whenever the reaction or the equation is given, please make sure the equation is balanced. Is it a balanced equation? Is it a balanced equation?
Yes, ma'am.
Okay, right. We take this equation as such. 2 moles of nitric oxide is reacting with 1 mole of bromine to give 2 moles of nitrosyl bromide. Okay, here, see, the question is when 0.087 mole of nitric oxide and 0.0 of Br2 are mixed in a closed container at a constant temperature. Initial number of moles of NO and Br2 are given, and 0.0518 mole of nitrosyl bromide is obtained at equilibrium. And they're asking us to calculate the equilibrium amount of NO and Br2. Okay. Before getting into all these data, let us have a proper assumptions here. When time t is equal to 0, let us assume the initial number of moles of nitric oxide taken is small a. Okay, so what is small a here? What is small a here? It is the number of moles of NO which was taken initially. So here it is in terms of number of moles and not the concentration, because here the question itself is in terms of number of moles, right? So here I've taken the hypothetical character which is small a. Similarly, small b amount of, that is number of moles of Br2 taken initially was small b. Since it is at the initial stage, reaction would have not started. So the number of moles of product formed is 0, right? But when the system is at equilibrium, a particular quantity of NO and particular quantity of Br2 would have involved in chemical reaction, right? And we don't know how much quantity was involved in the reaction, and similarly we don't know how much quantity of product formed also. So what I'm going to do is, from initial quantity or initial number of moles of NO, a particular number of moles would have been involved in the reaction, right? So let us take it as X, because we don't know how much quantity of NO was involved in the reaction. So hypothetically, I'm going to have it as X. But here, the number of moles of NO involved is 2 times. So what I'm going to do is A minus 2X. See, A is a reactant and this is giving a product B. Initial quantity taken was 100. So before the reaction started, the quantity of B is 0. But after a particular time, let us say 30 molecule of A was involved in the reaction. So how much quantity of product we'll be expecting? If 30 molecules of A was involved in the reaction, then what will be the number of molecules of B formed? Initially it was 100 molecules of B. I mean, initially 100 molecules of A, in which 30 molecules of A were involved in the reaction. So how much number of molecules of B you will be expecting at the product end? How much quantity kana? One molecule of A will get converted into one molecule of B. And what I'm quoting is, now 30 molecules of B was involved in the reaction. So how much quantity of B would have formed? 30, right? So number of molecules of reactant involved was similar to the number of molecules of product formed, right? So initially it was 100. Now 30 molecules was involved in the reaction. Could you please tell me the remaining quantity of A, which is the unreacted A molecule? How much it will be? 100 was the initial quantity in which 30 molecule was involved in the reaction. So what will be the remaining unreacted A? How much will be the unreacted A? Kana, you're getting my point. Bhumika, Sindhamichelvan. Initially, the quantity was 100 Kana, in which 30 was involved in the reaction. So, how much will be the remaining quantity of unreacted A? No, it is not 59, Sindhamichelvan. Actually, yes, it is 70 because initially it was 100. In 100 molecule, 30 was involved in the reaction. So unreacted molecule will be 70, right? How the 70 came? Initially it was 100 from which 30 was involved in the reaction. So 70 was the unreacted A. So how much quantity of B would have formed? Which is 30. Right. Similarly, this is the remaining quantity of nitric oxide. So initial quantity was A, from which 2x quantity was involved in the reaction. Why I have written 2x? Because here the number of moles of nitric oxide is 2. So I have written as 2x. Similarly, we have to find the remaining quantity of Br2. So this is the initial quantity, which is small b, from which X quantity was involved in the reaction. Here I've written only just X because here one molecule of Br2 was involved. So that is B minus 1X. So how much quantity of B would have formed? Here it is 2 times of X because here the number of mole is 2. That's it. So these are the number of moles of unreacted reactants and products. Okay, this is called as equilibrium mixture or equilibrium composition. Okay, here A, B, X were the hypothetical values. So now let us get into the problem. According to the question, 0.087 nitric oxide and 0.0437 moles of bromine are mixed in a closed container at a constant temperature. So what it means? Initial quantity or initial number of mole of nitric oxide and Br2 are given. So according to our assumption, small a is given as 0.087 mole and small b is given as 0.0437 mole, right? And what is the 0.0518 mole? Could you please tell me what is that 0.0518 mole? And now what is the 0.0518 mole? Please read the question. You can understand. Right. So, Sendamil Chelvan is right. So, this is the uh, number of moles of NOBr at equilibrium. So, which means here number of moles of NOBr at equilibrium is 2x. So, 2x value is given as 0.0518 mole. And what is the question? They're asking us to calculate the equilibrium amount of NO and Br2, which means they're asking us to calculate A minus 2x and B minus x. So we know the values of A and B, but we don't know the value of x, right? But we can calculate the value of x because 2x value is given, right? Now calculate the value of x, and from that value of x, please calculate the equilibrium amount of nitric oxide and Br2. Is it possible for you guys to calculate now? Can you please calculate now? So I want you to find the equilibrium amount of NO and Br2. So the equilibrium amount of NO is A minus 2x. We know the value of A, but we don't know the value of x. But we can calculate the value of x using the 2x value, right, which is given. Yes. Sendable Chelvan, your answer is 0.0352. What is that, Kana? What is that? Okay. So equilibrium concentration of NO is 0.0352 and Br2 is 0.0178. Right. Your answer is right. Then children's answer is right. Uh, how about rest of the students? You guys got the answer? So A minus 2x is the concentration, remaining number of moles of NO, which is 0.0352 mole, and B minus X is the remaining number of moles of Br2, 0.0178 mole. That's it. So what is the value of X? What was the value of X? Without calculating the X value, we cannot do it, right? Yes, 0.0259. Yes. So shall we move on to next question? Sharmila, Bhumika, Pushkan, shall we?
Yes, ma'am.
Okay. Any doubt till now?
No, ma'am.
Okay, fine. Now, next question. Reaction between nitrogen and oxygen takes place as follows. Here is the equation. Could you please tell me whether this is a balanced one?
Yes, ma'am.
Yes. So here, if a mixture of 0.482 mole of N2 and 0.933 mole of O2 is placed in 10-liter reaction vessel and allowed to form nitrous oxide at a temperature for which Kc is given, determine the composition of equilibrium mixture. So this problem is very similar to the previous problem. So we'll address the issue now. See, what is the question here? 2 moles of N2 plus 1 mole of O2 reacts with each other to form 2 moles of nitrous oxide. So let us have hypothetical parameters now. At time t is equal to 0, let us say small a is the number of moles of dinitrogen taken, and small b is the initial number of moles of oxygen taken, and since it is at the initial stage, product will be 0. When the system is at equilibrium, a particular quantity of A would have reacted in the reaction, right? So how much will be the remaining quantity? A minus, it should be 2x, right? Because the number of moles of nitrogen involved here is 2 moles. Similarly, it is B minus X. And what will be the product formed? What will be the number of moles formed? What will be the number of moles of nitrous oxide? Yes, it is 2x. Okay. Now they're asking us to find the equilibrium composition. So we have to find all the three values. Okay. And the data given is Kc. Kc is 2 into 10 power minus 37. Okay. So here A values and A value and B values are given. So A is the initial number of moles of nitrogen, which is given as 0.482, and B is the initial number of mole of oxygen, which is 0.933 mole. And there is also the value for volume capacity of the vessel, which is 10 liters. Okay. So Kana, what is Kc? Could you please write the expression for Kc? Because using this data we have to find the equilibrium composition, right? So for that, first of all, we have to write the expression for Kc. What is Kc? Constant product divided by reactant. So what is the product here? Kana? Expression.
N2.
Yes. So concentration of product divided by reactant. So here the product is nitrous oxide. So concentration of N2O power 2 divided by concentration of N2 power 2 into concentration of O2 at equilibrium. So in this expression we have to substitute the concentrations of all these species at equilibrium, right? But here the data given is just the number of moles and not the concentration. So we have to write or we have to substitute in terms of concentration. So have to convert number of moles to concentration. There is a relationship between number of moles and concentration. Concentration is equal to number of moles by volume. So we have to divide all the number of moles by volume to get concentration. Okay, right. So here A minus 2x is the remaining number of moles. So we have to divide it with V. Here also we have to divide it with V. Here also we have to divide V. That's it. So Kc is equal to, or Kc value is given. What is the value of Kc, Kanna? What is the value of Kc? 2 into 10 power minus 37, which is equal to, what is the concentration of nitrous oxide at equilibrium? It is 2x by V. What is V? It is the volume of the vessel, which is 10 liters whole square. And what is the remaining concentration of N2? What is the remaining concentration of N2 at equilibrium? A minus 2x divided by 10 liters, the whole square. And what is the remaining concentration, or the concentration of oxygen at equilibrium, which is B minus X divided by V, right? So V is the volume, which is 10 liters. So we know the values of A and B. We can substitute here and we can rearrange this expression and we can find the value of X. Using the value of X, we can find all the values here. We can find all the equilibrium composition. I mean, we can find the composition of this system, right? Also, here we can do one more thing, Kana. See, uh, it is easy to simplify this expression. And also we can do one more thing. What is the value of Kc? It is 2 into 10 power minus 37. Is it a small value or large value? Is it a small value or large value? Sorry?
Very small, ma'am.
Very small value. So what it means is, basically what is Kc? Concentration of product divided by reactant. So what it means, if Kc is very much less, then product would be, the concentration of product is very much less and concentration of the reactant is so much, right? So since the Kc value is very much less, what we can assume is the product formed is very much low, and here the number of moles of reactant involved in the reaction is also a small quantity, right? So what we can do is Here A is the initial concentration or initial number of moles of nitrogen, and from which 2x quantity was involved in the reaction. Since the Kc value is very much less, what we can assume is the quantity of nitrogen involved in the reaction was very much less. Actually, it is so insignificant. So this tends to 0. Similarly, here also x tends to 0, but you cannot tell 2x is 0 because the smaller quantity is formed, right? So we cannot have it as 0. But a minus 2x can be 0. Okay. So to make this numerical simple, I'm going to avoid this 2x and x term here. So 2 into 10 power minus 37, which is equal to 2x by 10 the whole square divided by a by 10. What is the value of a? Which is 0.482 divided by 10 the whole square. And what is the value of b, which is 0.933 divided by 10. So if you simplify this expression, you'll get the value of x. By using the value of x, we can find the equilibrium mixture, or you can find the composition of equilibrium mixture. Any doubt? Any doubt, Kana?
No, ma'am.
Okay. Please do this problem as activity. Now we'll move on to next concept, which is called reaction quotient. So we are done with equilibrium constant in terms of concentration and partial pressure. And we have seen the relationship between Kp and Kc also. Now we have two more subtopics in chemical equilibrium. One is reaction quotient, another one is Le Chatelier's principle. First is reaction quotient. Reaction quotient can be expressed in terms of QC. Okay, right. So basically, this reaction quotient is used to predict the direction of the reaction. See, for example, I have a reactant A, and this reactant A is getting converted into B. Initially, at time t is equal to 0, I've taken 100 molecules of A and the product didn't form yet. After 5 minutes, the concentration or the quantity of A was found to be 90 and product formed as 10. After 10 minutes, the quantity of A is 80 and B is 20. After 15 minutes, the quantity of A is 70 and this is 30. After 20 minutes, quantity of A is still 70 and this is 30. After 1 hour, the quantity is 70 and still it is 30. So what we can understand is at 15th minute, system attains its equilibrium, right? At 15th minute, equilibrium was attained. But before 15 minutes, so from 0th minute to 14 minutes, what happened? Reaction was happening or reaction was occurring in the forward direction only, right? For example, at 12th minute, what was the direction of the reaction? At 12th minute, what was the direction of the reaction?
Forward, ma'am.
Forward. See, I've given the proper data here. By using this data, we can predict at particular time what was the direction of the reaction. But practically in lab, we will not have this proper data, right? At any instant, we have to know whether the reaction is in equilibrium or the reaction is happening at forward or backward reaction. So for that, we're going to use the term QC. QC is very similar to your equilibrium constant Kc because the expression is quite similar. It is the concentration of product divided by concentration of reactant. But what is Kc? Expression is actually the same, right? Concentration of product divided by the concentration of reactant. But the concentration of product and reactant were at equilibrium. When the system is at equilibrium, At that time, the concentration of product and reactant were divided to find the value of Kc. But Qc is the concentration of product and reactant at any time, at any instant. Okay, so by comparing the value of QC with KC, we can find the direction of the reaction. The condition is if QC is less than KC, then the reaction is occurring at forward direction. If QC is equal to KC, then what we can understand, Kana? What we can understand? If they are equal, if they are equal, if QC is equal to KC, then what we can understand? The reaction is at equal.
equilibrium, ma'am.
If QC is greater than Kc, then we can understand the reaction is occurring at backward direction. Okay, that's it. So we may expect question from this concept also. They'll be asking us to find the direction of the reaction. Let us see one problem related to that. Here is the problem. A mixture of 1.57 mole of N2 and 1.92 mole of H2 and 8.13 mole of ammonia is introduced into 20-liter reaction vessel at 500 Kelvin. At this temperature, the equilibrium constant for this reaction is given as 1.7 into 10 power 2. Is the reaction mixture at equilibrium? If not, what is the direction of the reaction? So what we have to find? First, we have to find the value of QC, and we have to compare the value of QC with KC. So from the, using that comparison, we can find the direction of the reaction, right? So here at a particular instant, they have given you the number of moles of nitrogen, hydrogen and ammonia. So by using this number of moles and volume, we can find the concentration, and using that concentration, we can find the value of QC, and please compare the value of QC with KC to find the direction of the reaction. Okay. So what is QC? Concentration of product divided by reactant at any instant, right? So here the ammonia, your ammonia is the product divided by concentration of nitrogen into concentration of hydrogen, right, Kana? So what is the concentration of ammonia? Here number of moles of ammonia is given. So to find the concentration, we have to divide number of moles by volume. So here the number of moles of ammonia is 8.13 divided by volume of the reaction vessel is 20 liters. So 8.13 divided by 20, the whole square, divided by what is the number of moles of nitrogen, which is 1.57 divided by 20 into what is the number of moles of hydrogen, which is 1.92 divided by 20, the whole cube. That's it. So please simplify this and find the value of QC. Simplify this and please tell me the value of QC, Kana. Value of QC. approximate value is enough. First, cancel all
10.6, ma'am.
20s. Yes, Chelvan?
10.6, ma'am.
It is not 10.6. Do you have any 10 power terms? Please cancel all those 20s.
Two point one three into 10 power 3, ma'am.
Right. So 2.13 into 10 power 3. So this is the value of QC. Please compare this value with KC and let me know what is the direction of the reaction. So the condition is if QC is less than KC,
Backward,
reaction is
ma'am.
in forward. If QC is equal to KC, the reaction is at equilibrium. If QC is greater than KC, then reaction is occurring at backward direction. So what is the direction of the reaction now? Yes, it is backward because here 2.13 into 10 power 3 is the value of QC and KC is actually given as 1.7 into 10 power 2. So here QC is greater than KC, so the reaction is occurring at backward direction. That's it. Any doubt? Any doubt, Kanna? Okay. We'll do one more problem. After doing one problem, we'll move on to next concept. A sample of hydrogen iodide is placed in a flask at a pressure of zero point 0.2 atmosphere. Okay, in a flask they have taken hydrogen iodide compound and whose initial pressure was zero point 0.2 atmosphere. At equilibrium, the partial pressure of hydrogen iodide is found to be zero point 0.04 atmosphere, and they're asking us to find the Kp, and the equation is given. Please make sure the given equation is a balanced one. And we have to find the value of Kp. To find the value of Kp, please write the expression for Kp and substitute the values and let me know the final value of Kp. If you want clue, please let me know, I'll give you. What is the expression for Kp? Kp is equal to partial pressure of product divided by partial pressure of reactant. So here the products are hydrogen and iodine divided by partial pressure of hydrogen iodide, the whole square, right? At time t is equal to 0, what was the initial pressure of hydrogen iodide? It is given as 0.2 atmosphere. Since this is at the initial stage, pressure due to hydrogen and iodine will be 0. But when the system is at equilibrium, pressure due to hydrogen iodide would have been reduced, right? Because a particular quantity of hydrogen iodide would have involved in chemical reaction. So the remaining quantity or the remaining pressure due to hydrogen iodide will be 0.2 minus 2 times of P, right? Why I have written minus 2P? Because here 2 moles of hydrogen iodide was involved in the reaction, right, Kana? And actually it is given as 0.04 atmosphere. And here pressure due to hydrogen will be small p and pressure due to iodine will be small p. So find the value of Kp. See, according to this assumption, 0.2 minus 2p is 0.04, right? So from this we can find the value of p. So if we know the values of small p, then we know the value of partial pressure of hydrogen and iodine. We can substitute here in this expression and we can find the value of Kp. Could you please calculate the value of small p now? Could you please tell me the value of small p?
0.08, ma'am.
Yes. So value of small p is 0.08. So from the small p, we can find the value of equilibrium constant in terms of partial pressure.
0.16, ma'am.
Kana, can you please do it again? It is not 0.16. Sendam children, can you please do it again? It is not 0.16. Shall we do it together? See, what is Kp? It is the partial pressure of hydrogen at equilibrium into partial pressure of iodine at equilibrium divided by partial pressure of hydrogen iodide at equilibrium. Right? So,
4, ma'am.
sorry, Kanna.
Ma'am, KP is 4, ma'am.
Very good. Very good, Bhumika. Answer is 4. Fine. See, actually, Sandam Shelvan, shall we do it now? Actually, answer is 4 atmosphere.
Yes, ma'am.
So here, partial pressure of hydrogen is small p, and the value of small p is 0.08, which was right. The value you told me was right. And partial pressure of I2 is also small p, whose value is again 0.08. divided by what is the partial pressure of hydrogen iodide at equilibrium. It is already given in the question, which is 0.04, right? So 0.04 the whole square. So if you simplify this expression, you'll get the value of Kp. What was the mistake you have done, Kana? Okay. Any doubt? Any doubt?
No, ma'am.
Okay. Very good, Bhumika. Senthil Chelvan? Kana, what answer you are getting now?
4 ATM, ma'am.
4 ATM. That's it, Kana. So answer is 4 atmosphere. Super. Now we'll move on to next concept, which is called Le-Chatelier's principle, which is a very, very important topic in this chapter. See, according to Le-Chatelier's principle, whenever the system is at equilibrium, the system's temperature, pressure, concentrations of reactants and products, everything will be constant. When system is at equilibrium, temperature of the system, pressure of the system, concentrations of reactant product, everything will be constant. It will not change. If suppose if we disturb the system in terms of temperature or pressure or in terms of concentration, then this reaction itself will nullify that disturbance. That is called Le-Chatelier's principle. For example, when the system is at equilibrium, the equilibrium temperature was 35 degrees Celsius. This will not increase or decrease. Okay. If suppose I'm increasing the temperature by heating the system, I'm just increasing the temperature. So basically, what I'm doing is disturbing the system. So the reaction will nullify the disturbance. If suppose by heating the system, I'm rising the temperature from 35 to 80 degrees Celsius. So this is actually the disturbance. So this reaction, what it will do is, this reaction, it will move either forward or backward direction to make the temperature again to 35 degrees Celsius. So this is Le-Chatelier's principle. When the system is at equilibrium, equilibrium temperature, pressure, concentrations will be constant. Suppose if we do any kind of disturbance, if we give any kind of disturbance to the system, then that system itself will nullify the disturbance. This is called Le-Chatelier's principle. Now what we're going to do is, what all the disturbance can be given and how the disturbance are nullified by the reaction. We're going to discuss that. Okay. So first is disturbance in terms of temperature. A is my reactant, B is my product. So this is the forward reaction. Here B is the product and Q is the amount of heat energy released. So Kana, what is this forward reaction? Is it a forward, is it an exothermic or endothermic reaction? Here A is the reactant. This A reactant is getting converted into product B, and also it is giving out a particular amount of heat energy. So is it exothermic or endothermic? Yes, it is an exothermic reaction, right? Because a particular amount of heat energy is liberated out. As far as backward reaction is concerned, B is the reacting species and this is consuming a particular amount of heat energy, right? So here forward is exo, but backward is endo. Okay, here I've given you the hypothetical reaction, but what we can take is, whenever the forward reaction is exo, backward will be endo. If forward reaction is endo, then backward reaction will be exo. It will be just opposite. Okay, fine. For example, this reaction is at equilibrium, and the equilibrium temperature is 40 degrees Celsius. Okay. Now what I'm going to do is I'm just going to heat this mixture, and I'm bringing this 40 degrees Celsius to 60 degrees Celsius. So basically what I've done, I've just disturbed the system by rising the temperature. So what this reaction mixture will do, it will make the 60 degree again to 40 degrees Celsius. How it will do is, see, whenever you're rising the temperature, endothermic reaction will occur. What is endothermic reaction? It is the reaction, basically it will absorb a particular amount of heat energy to make the reaction happen, right? So whenever you're rising the temperature, this extra amount of heat energy was absorbed by the system to make the endothermic reaction to occur. So here extra 20 unit of heat energy was absorbed by the system, and again the temperature was 40 again, right? So whenever you're rising the temperature, endothermic reaction will happen. Here, according to this example, backward direction will backward reaction will occur and make the temperature again to 40. You're getting my point? If suppose if you decrease the temperature, then what will happen? For example, you're decreasing the 40 degree Celsius to 25 degrees Celsius. So which reaction will occur, Kana? What this reaction have to do? Again, this have to increase the temperature, right? Basically, what is exothermic reaction? Exothermic reaction will release a particular amount of heat energy, right? Now the temperature is 25 degrees Celsius. If the system releases a particular amount of heat energy, then again temperature will rise, right? So if you decrease the temperature, then exothermic reaction will happen, or it will occur to rise the temperature. So this is how the reaction will nullify the effect. You're getting my point? So if you increase the temperature, endothermic reaction will occur. If you decrease the temperature, exothermic reaction will occur. And here you cannot generalize whether the forward or the backward reaction will occur, because it depends. In some reaction, forward will be exo. In some reaction, forward will be endo. So we cannot generalize whether it will be forward or backward, but we can tell if you rise the temperature, endothermic reaction will occur, and if you decrease the temperature, exothermic reaction will occur. Okay. Any doubt? So this is all about disturbance in terms of temperature. Next, disturbance in terms of pressure. For example, A, reactant A is reacting with B. A is a gaseous reactant, B is also a gaseous reactant to give a gaseous product C. When the system is at equilibrium, the equilibrium pressure is, for example, 3 atmosphere. For example, this reaction is occurring, or I've kept in a cylinder whose volume can be adjusted. So this is a frictionless piston, right? The volume can be adjusted. So here I have a reactant A and B. Both are combining together to form a product C. And now the system is at equilibrium and the pressure of the system is 3 atmosphere. What I'm going to do is I'm just going to move the piston downwards. So if you're moving the piston downwards, what will happen to the volume? What will happen to the volume? Basically you're compressing the system, right? If you're compressing the cylinder, so what will happen to the volume and pressure?
Pressure increases, ma'am.
Yes, basically we are decreasing the volume, so pressure will get increased. So for example, from 3 atmosphere, pressure was raised to 5 atmosphere. Now the system is disturbed. So what will happen? Now this reaction has to nullify the effect. Basically, whenever the number of moles of gaseous species are more, then collision will be more. If collision between the gaseous molecules are more, then pressure will be more, right? Here I've increased the pressure from 3 atmosphere to 5 atmosphere. So what the system have to do? This have to reduce the pressure, right? How this reaction can reduce the pressure? This cannot move the piston, but instead this reaction can move either forward or backward direction. What it will do? Basically, number of moles of gaseous species will increase the pressure, right? But actually I've increased the pressure already. So what this reaction have to do? Reaction have to decrease the pressure. So to decrease the pressure, reaction have to decrease the gaseous number of moles. According to the example given, if the reaction is moving forward direction, then here 2 moles of reactant is getting converted into 1 mole of the product, right? So in this forward direction, number of moles of gaseous species is decreasing. And in backward direction, 1 mole of C is getting converted into 2 moles of A and B, right? So in backward direction, number of moles of gaseous species is increasing. So what this reaction will do, whenever you're increasing the pressure, the system have to decrease the pressure. So to decrease the pressure, reaction will move in a direction where gaseous number of moles are less. So according to this example, in which direction reaction will move to decrease the pressure? Is it forward or backward? In which direction reaction will move, Kanna? Because I've increased the pressure, right? So the reaction have to decrease the pressure. So to decrease the pressure, reaction have to move in a direction where gaseous number of moles are less.
Forward, ma'am.
That's it. Here also we cannot generalize whether it is forward or backward, but according to this example, the reaction will move forward direction to make the number of moles lesser. If you decrease the pressure, then reaction will move in a direction where gaseous number of moles are more. That's it. If suppose the reaction is like this, here both the sides equal number of gaseous species, right? So for this kind of reaction, pressure will not have any effect. That's it. So here, this is the disturbance in terms of temperature. Here, the disturbance in terms of pressure. Now we'll move on to disturbance in terms of concentration. See, we have discussed about a law called law of mass action. Do you remember? While we are deriving the equilibrium constant, we have talked about this law. According to this law of mass action, rate of the reaction is directly proportional to the concentration of the reactant, right? If you increase the concentration of the reactant, rate of the reaction will be more. What is rate of the reaction? Actually, it is the speed of the reaction, right, Kana? R is my reactant and P is my product. So this is the forward reaction and this is the backward reaction. So as far as forward reaction is concerned, rate of forward reaction is directly proportional to the reactant. Here, yeah, R is the reactant. As far as backward reaction is concerned, what is law of mass action? Rate of the reaction is directly proportional to the concentration of the product. But actually, as far as backward reaction is concerned, what is the reactant? What is it?
Product, ma'am.
Yes. So rate of backward reaction is directly proportional to the concentration of P. Right. Now, based on this law of mass action, we can understand how this reaction is nullifying the effect. When the system is at equilibrium, concentrations of reactant and product will be constant. Now, what I'm going to do is I'm just basically increasing the concentration of the reactant. If you increase the concentration of the reactant, in which direction reaction will move?
Forward, ma'am.
Forward, that's it. Or if you decrease the concentration of the product, if you decrease the concentration of the product, relatively concentration of the reactant is more, right? So either by decreasing the concentration of the product or by increasing the concentration of the reactant, you can make the reaction move in a forward direction. Okay. Similarly, if you increase the concentration of the product, then backward direction or backward reaction will occur, right? So either by increasing the concentration of the product or by decreasing the concentration of the reactant, reaction will move in a backward direction. That's it. So only in terms of concentration, you can generalize whether the reaction will happen, will occur in at forward or backward direction. But in terms of pressure and temperature, we can predict whether the exothermic endothermic reaction will occur or uh, direction of the reaction based on the gaseous number of moles. Only the disturbance in terms of concentration, we can predict whether the reaction will occur in forward or backward direction. Okay, that's it. So this is Lee Chartley's principle. Now we'll do a couple of problems under this topic. Here is the question. Does the number of moles of reaction products increases, decreases, or remain same when each of the following equilibria are subjected to a decrease in pressure by increase in volume? So what they are doing? See, they are basically increasing the volume. If you increase the volume, pressure will get decreased, right? So if you decrease the pressure, then what will happen to the concentration of the product? We have to predict whether it will increase, decrease, or there will not be any change in the concentration of the product. So what is the rule? If you increase the pressure, reaction will move in a direction where gaseous number of moles are less. If you decrease the pressure, reaction will move in a direction where gaseous number of moles are more. So based on this rule, you have to find in which direction reaction will move. Based on the direction of the reaction, you have to predict whether the product is increasing, decreasing, or there is no change in the concentration of the product. So, what is the answer to the first question?
First
In
one increases, ma'am.
okay,
Decreases and remains, ma'am.
so here increases, and in second question or in second reaction,
Decreases, ma'am.
decreases. In third reaction,
Remains same, ma'am.
very good, Kana. Could you please justify your answer?
Ma'am, in first reaction, the products are both in gaseous state, ma'am.
Hmm.
In second, only the reactant is in gaseous phase, ma'am.
Hmm.
And in last, ma'am, both product and reactants have same number of gaseous phase, ma'am.
Okay. So, in first reaction, in reactant side, we have only 1 mole of gaseous reactant. Here, we have 2 moles of gaseous product. In second reaction, we have 1 mole of gaseous reactant and there is no gaseous product. And in a third reaction, we have 4 moles of gaseous reactant and 4 moles of gaseous product. Now they are decreasing the pressure. If you decrease the pressure, reaction will move in a direction where gaseous number of moles are more. In first reaction, which side the gaseous number of moles are more? In second, I mean, at the product end, right? So the reaction will move in a forward direction. So due to which concentration of product will get increased. Okay. And in second reaction, number of moles of gaseous species are greater at the reactant end. So reaction will move in a backward direction, because of which the concentration of product will be decreased. And here there is no difference in the number of moles of reactant and product. So if you change the pressure also, there will not be any effect on the concentrations of reactant and product. So here the concentration of product remains same. Very good. Now we'll move on to next question. Here is the question, Kana. Which of the following reaction will get affected by increasing the pressure? Also mention whether change will cause the reaction to go into forward or backward direction. So what is the answer for first question? Basically they're increasing the pressure, right? So what is the condition? If you increase the pressure, reaction will move in a direction where gaseous number of moles are lesser. If you decrease the pressure, the reaction will move in a direction where number of moles of gaseous species are more.
Backward, ma'am.
Why it is backward? Your answer is right. I just want the justifications and the
Ma'am,
children.
if you increase the pressure, the volume will decrease, ma'am.
Okay.
And also, if you have more gaseous products, it will release more partial pressure, ma'am.
Okay.
In the reactant side, ma'am, there is less gaseous atoms, ma'am.
Hmm.
So the pressure will be low, ma'am.
Okay. So, if you increase the pressure, reaction will move in a direction where the gaseous number of moles are lesser. In first equation, at the reactant side, we have only 1 mole of gaseous reactant, and in product side, we have 2 moles of gaseous products, right? So here you're increasing the pressure, so reaction will move in a direction where gaseous number of moles are lesser. So here reactant side, the number of moles of gaseous species is less, so the reaction will move in a backward direction. That's it. So the second question. Second question.
Backward, ma'am. No change, ma'am.
No change, because here both reactant and product got equal number of gaseous species. So if you change the pressure also, there will not be any impact. So no change. It will not cause any change here. In third reaction, in reactant side we have only 1 mole of gaseous species, and react product side we have 2 moles. So in which direction reaction will move?
Backward, ma'am.
Very good, backward, Kanna. Okay. Fourth question.
Forward, ma'am.
Very good, Kanna.
Forward, ma'am.
Here, reactant side we have 3 moles, and in product side we have 1 mole. So here, forward reaction will occur. Super. Fifth one.
Backward, ma'am.
Yes, backward, because reactant side we have 0 moles of gaseous species. Here 1 mole. So backward reaction will occur to reduce the number of moles of gaseous species. And in sixth reaction,
Backward, ma'am.
yes, backward, because left side we have 9 moles of gaseous species, and right side we have 10 moles. So backward reaction will occur to reduce the gaseous number of species. That's it. We'll do one last problem, okay? Based on Lee-Hartley's principle, one last problem. Describe the effect of addition of hydrogen, addition of methanol, addition of removal of carbon monoxide, removal of methanol on the equilibrium of the reaction. They have given you the equilibrium reaction, and they're asking us to find what kind of effect we can, or what kind of change we can observe by adding or removing these chemical species. This is also from Lee-Hartley's principle, of course.
Ma'am, the equilibrium shift towards right, ma'am.
Okay, why?
As we increase the concentration of product, it increases the forward reaction, ma'am.
Here, hydrogen is the reactant, and if you increase the concentration of the reactant or if you decrease the concentration of the product, forward reaction will occur. And if you increase the concentration of the product or if you decrease the concentration of the reactant, backward reaction will occur. Right? Okay, here hydrogen is the reactant. So basically, you are increasing the concentration of the reactant. So a forward reaction will occur. So reaction will move right side. Okay. Next, second question. Addition of methanol. Methanol is, what is methanol? It is a product. So you're increasing the concentration of the product. So in which direction reaction will move?
Backward, ma'am.
Backward. Very good. Backward. Okay. Third question. Removal of carbon monoxide. Carbon monoxide is the reactant, and if you decrease
Forward,
the concentration of the reactant, then
backward, ma'am.
yes, reaction will move in a backward direction. And this question.
Forward, ma'am.
Yes, here they are removing methanol. Methanol is product. So basically we are decreasing the concentration of the product. By decreasing the concentration of the product, reaction will move in forward direction. That's it, Kana. So we are done with chemical equilibrium. We have discussed all the subtopics under chemical equilibrium. In next class, we'll be starting ionic equilibrium, where we'll be discussing a lot of concepts related to pH and pOH, which is a very, very important topic under equilibrium. So I want you guys to do this problem as activity. This is basically based on Lee-Chartiers principle, I guess. So please do this problem as activity, and in next class we'll be discussing ionic equilibrium. Okay. And try to solve all your NCRT problem related to chemical equilibrium. Actually, there are around 30-35 problems under chemical equilibrium. Few problems we have discussed already. Okay. Please solve rest of the problems under chemical